So the second part of the lecture for today is about tabular data. So how is that different from what we've done? Basically, in t-test we looked at two groups. But what we looked at comparing there was that we had real numbers of observations in each group. We did not care so much about how many were in each group. We like if there are about equally many everywhere, but it's not needed. So when you do tabular data, then what you do is that you classify observations. So rather than having a real number, you classify it. So it could be, if you have two outcomes, you can have a binomial distribution saying, well, if you have a die, what is the odds of having a 6 whenever you throw it? Probably 1/6, unless the die is not fair. I can pick up one of those from my neighbor here, where you have kind of the odds of getting a 6 is around 5/6. You can feel it when you have it in your hand, that is different. If you want to feel what it is, I can bring it. Just for fun. So then you should pick the right game before starting. But what happens is when you can say for the binomial distribution, if you have a large sample, then you can, and the probability is not too close to 0 or too close to 1, then you can approximate it with a normal distribution. I assume you looked at that in the Introduction to Statistics course. But just a quick recap. That normal distribution, if you have x as a binomial with n observation and p as probability, what is the mean value of x? And what is the variance? Let me write it as sigma square x. Do you recall that for binomial distribution? It may be a long time ago, but those are some of those small things that's good to know. What is the expected value? Yes? N times p, exactly. And what is the variance? It starts with the same, but has a little bit more. Anyone? Yes? No, not quite. It's n times p times, yes? 1 minus p, exactly. So that's the variance, the mean value, and if you use that in a normal distribution, that actually works out if n times p is sufficiently large and p is kind of not too close to either 0 and 1. I think typically you say if n times p is 15 and less than n minus 15, then it's okay. And the closer p is to 0.5, the better the approximation. So a classical example to get a Nobel Prize, I think you need to do a little bit more today. So vitamin C, does that have any effect on getting a common cold? That's the underlying question. And how you do that in a medical study is that you take a number of volunteers, in this case 818, and then you randomly assign them to two groups, those that receive a placebo and those that receive vitamin C. Now, this experiment was so-called double-blinded, which means that neither the volunteers nor the physicians who examined the volunteers and thereby also gave them the drug they were getting knew which treatment they were getting. So it's only the one who was, you can say, making the experiment, but he did not tell the ones who actually saw the patients. Because otherwise, you know, the placebo effect is quite dominant. And if you can see that, sorry, you're getting this pill, But hey, you got this one. Probably the one receiving it. So whenever you do medical studies, typically they are so-called double-blinded. This is the outcome. Counts, 335 got the placebo and got a cold. 76 didn't get a cold, still got the placebo, and so forth. And it's quite custom that you add the row and column sums and the total sum down there just to check that everything add up. So, does anyone recall what to do with such things? Chi-square test, yes. Does anyone recall what a chi-square test does? So what you're looking at is in each of the cells, of the 4 cells in here, you have to look at what is the observed value minus what is the expected value. You square that and divide it by the expected, and you sum that over all cells. Chi-square distribution, do you recall where that comes from? It comes from a sum of squared standard normal distributions. So you consider this out here as a squared epsilon, a squared error. So sometimes you see the observed minus expected divided by the square root of the expected. That's the residual. And then there's the other thing, that is the number, when you look up the chi-square distribution, how many degrees of freedom should you use? Number of rows minus 1 times the number of columns minus 1. And why is then that? That means how many degrees of freedom do I have in this case? Well, 2 minus 1, that's 1, times 2 minus 1, that's again 1. 1 times 1, 1. So that's the easy one. Now, why do we use the number of rows minus 1 and columns minus 1? That's because we condition on the sums out here. Because in the design of the experiment, we make sure that we assigned 411 to the placebo and 407 to the vitamin C. And that means if this sum here is given, and you found that 335 got a cold, well, then there has to be 76 that did not get a cold. Now, if the column sum is also given that those two numbers here are now calculated, and the sum are given, then those two numbers are also given. So that's only when the row and column totals are given, you only have one number that you can pick. All the rest are then given. That's the idea by how you calculate. So if you add an extra dimension, we'll do that later, then of course you get more degrees of freedom. If you get an extra column, so you have 3 columns and 2 rows, then you have 3 minus 1, that's 2, again times 1. So then you have 2 degrees of freedom. Oop. That's what I wanted to be, sorry. So what is missing in order to do this? We have the observed sum of observed minus expected squared divided by the expected. How do we calculate the expected value in such a table? Maybe a long time ago. Think for 2 seconds. What is it that we are after? We assigned 411 out of the 818 to the placebo group. So we expect that a little more than half of those that got a cold those that get a cold down here, we expect that a little bit more than half came from the placebo group and a little less than half came from the vitamin C group. Because 411 over 818 times this number down here. That gives the expected number up there. Does that make sense? So you take, in this case here, to get the expected number for placebo and cold, you say that you have 411 that got placebo out of 818. So that's the fraction of the 637 that you expect. So if that is a fraction, you multiply by how many there are that got a cold, then you got the expected in the cold placebo number. I can't do this by heart, but R can help us. 411 divided by 88 and then multiply by 637. So the expected value here is 320.0 or 0.1. What we observed was 335. So here we have a residual of 15 in that group. We do the same in all the others. The easy way to remember this is that what you do is that you have row 1, row 2, column 1, column 2, the sum for the rows and columns, and then you have the total down here. To get the elements in here, you just take the product of row 1 and column 1 divided by total. So you take the product of the number of the row sum and column sum and divide by total. And you just do that everywhere. That's effectively what we did here for the first element. So that's how we do things. And we take the vitamin C data. Let me go back. Have it here. So I can make a matrix here containing the numbers. Here's one way of entering a matrix. It's not so straightforward to see what happens. I'll give you that. So therefore I'll just explain it. I took the numbers here as a vector, and I say I want to have 2 columns with 4 elements that also give me 2 rows. That's obvious. What is maybe not so obvious is where to place the second element. Should that go in the bottom left or top right corner? So what R does is that it stores a matrix column-wise, not row-wise. So if I make a matrix here of the numbers from, say, 1 to 12, and say I want to have 3 columns, then I get the numbers 1, 2, 3, 4 in the first column, and then 5 through 8 in the second column, and 9 through 12 in the third column. So that's how, but I could also, there's an option here, if you wanted to have it row-wise instead, because that's how you get the data as input, you can say by row equals true. Then of course, you get 1, 2, 3 in the first row, and so forth. But the default is to have data stored column-wise. Just to tease you a little bit, if I take this one here, and say now I don't want it as a matrix. I should be nice. So I have temp, which is this matrix. Now if I take this as dot numeric, then I get the observations the way they are stored in there, not the way I put them in. I see someone being, it's January 2nd, but it's obvious what happened, right? You have the first 4 elements, that's the first column, and then you take the second column and the third column. So internally, they are stored column-wise. You specify how, when you create the matrix, you specify where you put them, but they're always stored column-wise. So that's good to know. And then up here, I give the extra argument dimension names, first for the rows and then for the columns. Typically, I would probably myself just create a matrix first without any names, and then I'll give the dimension names afterwards as the same list as argument up there. So that's the data I have. And the chi-square test is one of the easy things to do. You give it a matrix, and then it just runs the test. So the question is there a significant interaction? Yes, there is, because the p-value is less than 5%. So that's the conclusion in this case. I discussed one thing with some of you in the morning about what the difference between R and MATLAB. And one of the things is that things are objects. So if you look at this object here, what does it actually contain? It contains a number of elements. It's a list containing different elements. I haven't done this for this data. Getting the string representation, then it shows us what is also the content of every element in here. So what is the statistic? How many degrees of freedoms do we have? What is the p-value? What was the method? Where does the data come from? What was the data? Here are the expected numbers, the 320.1. And the residuals here are, you can say, the residuals from there, and so forth. Or I could just get the residuals like this. It was a residual of 15 divided by the square root of the expected. The square root of 320. That's roughly 18. How close was I? 17.9. Okay. So that means 15 divided by 18. That's the 0.83 here that we have. So that was just to get one of the residuals, and the same thing for all the other cells. So we could say we have the observed minus the expected, and then divided by the square root of the expected to get that number. That was the same thing I just did, to look at what is the content in there. It also means that if you're running the test and you only want the p-value out, because you're running many tests, you can just say that I want the p-value, and then you just get the number. But you're indexing it just like a data frame where you take the columns. A data frame is also a list of vectors in a data frame. Here is just a list of various different components. Now that was one way of doing this. Often you do not get data that are pre-counted. What you get is a table. So you get a file with some observations in it. Let me just open the file. I'm in the wrong folder. So I have this. The first column is just an ID. Then I have vitamin C and cold, and or not cold, whatever. So I have one column for each of these three things. And I have a separator here that is a comma. And now I have to remember to set the Let me get an error first. Cannot open file, no such file directory. Many of you saw this morning as well, and it's basically because you're in the wrong folder. If you have a script that is saved in the folder where you want to be, let me just save it. Then picking session, set working directory to source file location typically helps. Let's try it again. It still fails. It says more columns than column names. This error and similar errors are because when I try to read in the default for read table here, let me just the default, let me just hit F1. The default separator between columns here is given as the empty text string, which means any blank character. That means a space or a tabulator. If you look at the content of the file, there are no spaces in the first row, but already in the second row there's a space there. So we'll try to read it with only one observation in the first line and two in the second. Then there are two spaces in the third line and so forth. Doesn't make any sense. So we have to specify which separator to use between columns. And I will test you at some point where things will not just work by default because I changed the separator. So far, I think you'll be able to just load the data without specifying the separator. Also, if you have data that are from a Danish computer, so the decimal point is a comma, there's also an option here to give dec as decimal point. In this file, it's just a period. And now I have it. Now, the first row names there, I actually don't want that. Those are just IDs of the individuals. So I can specify I want to use the first column as my row names. So now I only have, I got 411 that got placebo, 407 that got vitamin C, and similar numbers for cold. This is not the table that we need. This is not cross-tabulated. These are just how many are there. These are the row and column totals. I can make a table of it, which is the same as what was there before. And I can use the chi-square test as we did before on the table, but you can also just give it as two factors, because what is in here, when it gets text as input, it will automatically convert it to a factor. So we have placebo or vitamin C, and when you have chi-square test, if you get two vectors or factors, it will automatically create the table and do the chi-square test. So everything here does the same thing. Now, we were told that there was a significant interaction here between the two. One way of looking at that is the so-called mosaic plot. Here, it's not so visible. Everything that is a full drawn line around is overrepresented. Everything that's a dashed line around is underrepresented. And the fill color gives you the degree. The default is to use 2 and 4 as split points between the colors. So what we can see here is that all residuals are less than 2. What we do see is, it's not so easy here, maybe if I will, this doesn't change a thing for the colors. I will just transpose the table. So what happens here in the mosaic plot is that the area of each of these cells represents how many are there in that group. The width of the columns specify the fraction of those that got cold versus not cold. So that there's always going to be a gap there all the way through. Now, if there's no difference, that box and that box will have the same height, which they obviously don't. So here's easy to see that they are overrepresented here because there's more that got cold among those that got placebo than not cold among placebo. And vice versa for those that got vitamin C. Does that make sense? The important thing is to remember area equals numbers or count in each group, and then you can look at the outline to see what is over and under. This is an easy case where there's only 1 degree of freedom. It's a 2 by 2 table. I will show you one that is a little bit more complicated in a moment. So, in this case, we had many observations in each group. Everything is fine. The chi-square test is good. However, if the expected count in a group or in a combination is less than 5, then the assumption of these residuals to be normally distributed doesn't hold anymore. It's roughly around 5. 5 is not a sharp number, but that's the threshold that is generally agreed on using. In that case, there's a so-called Fisher exact test. Basically, what it does is that it tries all combinations that you can make. How many ways, and then looks at how extreme is the observed outcome relative to all other combinations that can be made of that. It tries to enumerate all options. So it doesn't work in case there are too many persons in a study. And we looked at a 2 by 2 case, discussed if you have more than 2 by 2, it's not that difficult. You do the same thing. It's always the row and column margins multiplied together, divided by the total sum. That's the number of elements, participants, sorry. That's the expected number, and you can do this for the entire table. You can also do it in higher dimensions. Now we've done it in 2 dimensions, but what if you have a third classifier or fourth? It's not a problem. As long as you have an observed count in each cell, then you can do it. Does it also work in 1D? Yes, it does. So if you have some data, you want to test an assumption about, say, distribution, one way to do it is not the most powerful way, but one way to do it is to make a histogram and look at, well, how many do I expect in each bin and how many was actually in each bin in the histogram. That works fine. You have to think a little bit further if you do stuff like that, because sometimes you will end up estimating some parameters. And just like when you do linear regression, if you start estimating parameters, you use degrees of freedom. So in the case where you want to, say, compare with a normal distribution, how many do you expect? First you estimate a mean value, and you estimate the standard deviation as well. So you estimate 2 parameters, and you know that if you have a histogram, let me just add it on top here. Let's say it looked like this. The question is, does that actually come from that normal distribution, assuming with that mean and standard deviation? Maybe I need some extra out here to have the same mean and standard deviation, something like that. It will work. So is that likely to happen? Well, then you look at how many were in each count. Also, I have 1, 2, 3, 4, 5, 6 bins here. But I also have a bin down here that is 0, and a bin out there that is 0. So right there I have 8 bins. So how many degrees of freedom should I compare with when I do the chi-square test? It's always, in the 2 by 2 case, it's the number of rows minus 1 times the number of columns minus 1. Because the total number of observations is fixed. So here, it is the degrees of freedom. We start out with 8 counts. Then we subtract 1 because the total sum has to be given. But we also estimated both a mean value and a standard deviation, so we subtract 2 more to get 5. In this case, does that make sense? Somewhat? Typically, if you just have 8 counts, so we have 0 in this case, let's make that a 5 and a 8, 3, 5, 3, 7, and 0. Those are the count in the bin. So basically, this corresponds to having a table with a 0, a 5, 8, 3, 5, 3, 7, and a 0. And then, I haven't done the total while I did this. That's 10 plus 21. So the total sum here is 29. And you can find the expected value by saying that given that I have 29 observations, what is then the likelihood of observing something that is less than this? What is the likelihood of being out here times 29? What is the likelihood of being in this interval times 29? And so forth. In that way, you can get an expected count. So you get the expected count by looking at the white line behind and looking at the cumulative distribution function for that. We'll discuss it closer tomorrow because this is part of one of the last exercise for today. But now you know what you need to know to solve it. I'll discuss it later in details. So, just to show you something that is more than just a 2 by 2 table, we will look at homicides over a 10-year period in Canada. And what we look at is the parent-offspring sex combinations to look at is there anything that is overrepresented or not. So the combination here is, the letter here indicates that it's a male father and a male son. So the uppercase letter here indicates the adult, and the lowercase first letter indicates the child. So there were 24 boys between the age of 1 that were killed by their father, while there were 53 boys below the age of 1 that were killed by their mother over this 10-year period in Canada. I know the data is not too fun to think of, but it's a nice data set. Now, if we look at this, and then it's, you could say, done in different age groups. If we take the data, I've just entered it manually, like this, and I label them as year old for 17 and above. So I just gave the upper bound for each of the groups. So this is 0 to 1, 1 to 5, and so forth, years of age. I just gave the upper bound for each age group. And then letters again, male, fathers to sons, fathers to daughters, mothers to sons, mothers to daughters. There's an add margins function if you want to kind of do everything manually. It's not so fun. But one thing to consider here is the chi-square approximation actually fulfilled? The easiest way to do that is to just run the test. Don't look at the p-value just now. Look at the expected values in every cell, because it's calculated from there. You don't have to do it manually. That's always nice. And you look at, well, all the expected values here are 10 and beyond. So that means they're also greater than 5. Now we can go back and look at the test. The p-value is very, very, very small. So we can look at the standardized residuals here, the Pearson residuals. Observed minus expected divided by the square root of expected. And then we look at the numbers here, we see that, well, there's something for the old over here. There's really something happening over here, right? So the mothers are underrepresented, but the fathers are overrepresented, whereas for the infants, it's reverse. Because you have large positive numbers there for the mothers. And if we do this, let me just zoom in. We see the same pattern here. If you look at the 1-year-old, or less than 1-year-old, then the fathers are underrepresented in killing their sons and underrepresented in killing their daughters, but the mothers are highly overrepresented. Actually, the mothers are killing more infants, or about as many infants, as the fathers are killing below the age of 10. But reverse holds for father killing their adult sons, whereas the mothers does not kill their adult sons. Only sometimes their daughters, but they're still also underrepresented. I know it's absurd, these data sets here, but I think it's very nice to show, and then you can discuss what are the reasons for this. What did we learn from this? I'm not into social scientists, so I won't comment further on that. But it is a way to kind of get a very clear picture as to where does things happen. What is the most bright colors in this case? Focus on what is the meaning of being overrepresented here and there. And of course, if something is overrepresented somewhere, there has to be something that is underrepresented elsewhere. That's kind of obvious. That's the same plot that I included in the slides. Just for the fun of it, trying to run the Fisher exact test, if we had not looked at the expected, it will fail with a comment on that I don't have enough memory. Because the total count, let me just go back and look at that. We have 525 in here. How many degrees of freedom do you have in this model? I think this is one of those where I give you 30 seconds and then I will ask for an answer. Are you ready? 1, 2, 3. With an echo as well. I didn't hear anything but 12, so I'm happy. Anyone not understanding why 4 times 3 is 12? Now, probably not. Why is it 4 times 3? Because we have 5 age groups and 4 sex combinations, and 5 minus 1 times 4 minus 1, that's 12. I was teasing you a little bit by showing you the one with margins added here. Because there I have an extra, there I have 6. But that's because I added the margins. So with 12 degrees of freedom, how many ways can you distribute those 500 and something among all those 12? Just figure out what the combination is there. You don't want to number all those possible combinations. If we just take the homicide and take a fraction of the table, just taking all the 4 columns and just looking at, all the 4 rows and looking at just the 2 large age groups. So then the total count is not so big. Then it can run. Even though the sum here is still almost 200, but the degrees of freedom now is only 3. So the number of combinations of where to place those 200 is not so huge. An alternative, if you want to do something different, just showing the data again, if the expected was also too low down here, one way that you can do that is to kind of just bin things together and say, rather than having, say, both those that are 11 to 16 and 17 and older, rather than having those as 2 groups, you can just combine it into 1 group. So I will leave out the 4th column. When I index with a negative number, I get everything but that column. And then I can say that, in this case, I want to add the smallest number, the one that is closest to. I want to add the Y10 and Y16. So then I take and make the 3rd column in this, the sum of the 3rd and 4th column in the original data. So now I have this. Then I should make sure that I relabel this one here to have the appropriate label. So now it looks like this. Now all the observations are also above 5. They don't have to be, it's the expected number that has to be. But if all observations have count above 5, then there's no doubt that the expectation will also be above 5. And again, it's highly significant. And if I look at the mosaic plot, it didn't change much. I only grouped things a little bit. Now, I will just, to exemplify, transpose this again. To show the difference. So, cannot do that when not zoomed. Let me just trim the plot a little bit first. I want no space, nowhere. That may be pushing it too much. Let me have a little space at the top. Then I have everything inside, because mosaic plot kind of redraws everything on its own. So this is the transpose. If I remove the transpose, I flip things. The colors and the size of things are the same. All boxes have the same area as before, because the area represents persons. But you say, what is your interest? Is it mostly the age groups, or is it mostly the sexes? Typically, it's nice to have the columns as being the variable that you want to infer about. So here we can look at, it's easy to see that we have the same width for all the infants being overrepresented, underrepresented with fathers and overrepresented with mothers. It's the same thing we see, here was just the first row. But sometimes it's easier to explain what happens if you transpose it. It depends on which story you want to tell. I find it easier to look in columns when I look in a plot like this, because they have the same width. But that's a subjective thing. So how far did you get with the exercises?